Good afternoon, ladies and gentlemen. Welcome here at the Technical Forum at the group exhibit Hydrogen, Fuel Cells and Batteries. This year, in the year of 2015, at the Hanover Fairground. Every 15 minutes, you will hear interesting presentations regarding the hydrogen industry. Our overall today topic is hydrogen production and energy storage. My next presenter will discuss the topic lifetime testing of PEM fuel cells. And for that, please welcome with me on stage head of the Fuel Cell Department of the Fraunhofer-Institut für Solare Energiesysteme, Mr. Groos. Big hands, please.
Thank you very much. Thank you very much and welcome. So, yes, as she told you, I'd like to talk about lifetime testing of PEM fuel cells and address several aspects in doing these degradation tests. So first of all, the Fraunhofer Institute for Solar Energy Systems, we work and live in Freiburg, which is in the very south of Germany. We are the largest institute for solar energy systems in Europe and maybe worldwide, with 1,300 heads counted. And my department, Fuel Cell Systems, has around 30 people working on PEM fuel cells. So we address several markets, automotive markets, portable energy, maybe uninterruptible power supply, and also microfuel cells. We work, as Fraunhofer Institute, we work strongly together with industry, so we are very well connected all over the world, and due to the reason that we have a strong focus on automotive applications, we established some strong cooperations with Canadian institutes and Canadian companies. So, but that's for the moment enough about Fraunhofer ISE and my department. I'd like to talk about the topic of degradation of PEM fuel cells, and degradation of PEM fuel cells has various aspects or can be caused by different sources. So one aspect of degradation is that degradation is caused by the operation itself. So maybe you have several dynamic load changes or whatever. Second, degradation can be caused by the cell components itself. So maybe you have a metallic bipolar plate and corrosion occurs. Or you see degradation of the peripheral elements, where also corrosion can occur, and the cations can harm, for example, the membrane. Then, of course, a fuel cell is operated in the real world, and so there are environmental conditions like high temperatures or freezing temperatures, which can cause degradation of the PEM fuel cell. And last but not least, you have contamination, for example, by the air, or contamination by the fuel itself, by the hydrogen. So these all are several aspects which terminate or define the end of the fuel cell and cause degradation. And if you do lifetime testing, you should take care of all these aspects. Another issue is on what level you do your lifetime testing. So we do lifetime testing, for example, with real fuel cell systems in their application. And as one example, we are testing the B-class F-cell of Daimler for over 3 years now, and we extended this monitoring for 2 other years. We are very proud that we have this possibility, which is mainly due to the fact that we have our own solar hydrogen filling station, so refilling of the cars is very easy for us. If you look at the system level, you should always take care of the peripheral elements itself. So as one example, we test the lifetime of the peripheral elements of a fuel cell system. And one example was this, that we did some long-term testing, some cycle testing of valves under different climate conditions. This was lifetime testing of valves, but I said before that also corrosion can occur in these peripheral elements, and we do investigations on that. Maybe that you insert these, in this picture is shown a valve, you insert this valve into an acidic solution which is or simulates the conditions inside a fuel cell system, or if the elements are in contact with power, you can apply also potential, and then you do a corrosion current testing, for example. When you do that, it's very interesting to look at the solution itself. So what elements do you find after this testing of the peripheral elements in the solution? One example for system testing is that you collect the product water and then you do some mass spectroscopy. We have an ICP-MS, which is an inductively coupled plasma mass spectroscopy, and then we can analyze the elements that you find in the product water. Or with the example before, for the testing of valves in solutions, in acidic solutions, you test and look at the solution and see what elements you find inside there. This was testing on a system level, but if you go one level below, you look at the stack level. So what we do is that we have a running project where we do tests over 10,000 hours on a stack level, and we are testing 9 stacks in parallel at different load profiles. So 9 load profiles with 9 stacks all together, and all of these stacks will be operated about 10,000 hours. And then you learn a lot about degradation of these stacks. If you do these tests in the picture before, you saw the laboratory environment, but I told you before the real fuel cells are operated in the real world, so it might be very, very hot, or the opposite, it might be freezing temperatures. So you should also think of doing lifetime testing under real environmental conditions. If you do tests on a stack level, then it's worth to think of what happens inside a stack and what are the main questions. So if you look at the stack, at these schematics, the single cells are stacked on top of each other. Then you have a hydrogen inlet, and hydrogen is anyhow distributed over the cells. Anyhow means it depends on the pressure drop within a single cell, which flow of hydrogen you realize in a single cell. And this is very difficult to calculate and very difficult to measure. The pressure drop depends, of course, on the geometry of the channels and the windings and so on, but it depends very much on the humidification of the stack and the cell itself, because humid membrane will swell, and if the membrane dries out, it will shrink. So you have swelling and shrinking, and the humidification of the membrane is the reason for that. Humidification depends very much on the current that is produced within the cell. And the current, again, depends very much on the gas supply which is in the cell. And the gas supply, again, depends on the pressure drop. So it's all is depending on each other. So it is very, very difficult to really calculate or to measure the hydrogen distribution within a stack. And the same is with the air. And then you have the cooling flow. The cooling flow is even more complicated in a way, because the cooling flow field with metallic bipolar plates, it's not a real flow field, it's the result of the backside of the anode flow field and the backside of the cathode flow field, at least with metallic bipolar plates. So how the cooling liquid is distributed within the cells is also not very easy to define. Last but not least, the stack is clamped and a pressure is put on the stack so that you have a good mechanical contact and electrical contact of all these components of a stack. And this clamping pressure is very well defined at the beginning of the stack, at the initial operation, but then it depends, the internal pressure distribution depends very much, again, on the membrane behavior, on the swelling and shrinking of the membrane. So one main question that we like to address is if you really know what's happening inside your fuel cell stack. And to investigate this, we have a really special setup at our institute. So you remember the question of the different climates. So we can simulate very hot temperatures up to plus 80 degrees Celsius and freezing temperatures down to minus 40 degrees Celsius with, if you have plus degree Celsius, with a very well-defined humidification of 5% up to 95%. And then we have, you see it in the back, we have a test stand with us able to cover stack powers up to 20 kilowatt. But what is really special in this setup is this black case that you see in the middle of the picture. This black case has up to 50 channels, and we can connect with this measurement equipment every single cell. So we can measure the single cell voltage simultaneously, which is not very special, but what is really special about this technique is that we can do characterization of the single cell impedance spectroscopy simultaneously with up to 50 cells. And with this technique you get pictures like that. So we did this for a Daimler stack AFCC, so a real automotive stack with 20 cells in this case. And what you see is the distribution of the impedance spectra. You see with the bold lines the average impedance of a single cell, and then a little bit lighter you see the maximum impedance spectra and the minimum impedance spectra. From the impedance you can learn a lot about the behavior, about the heart pulse of the cell. And in comparison you can learn a lot about the distribution of gases inside the stack and differences about the single cells within one stack. So this was about the cell stack level. So now I'd like to come to the cell level. In the cell again you have a distribution of gases. So for example hydrogen is flows over the active area of the single cell and is distributed, and with a reaction of course the reactants are the concentration will vary over the active area, the concentration of the reactants due to the reaction itself, and due to the reaction water is produced, so humidity will change over the active area, and due to the reaction of course heat is released, so temperature will vary. The variation of the temperature depends very much of course on the cooling flow and cooling distribution. So understanding local effects on a single cell level is a very important issue for us to improve your cell design and operating strategy. We do that, so again you see a distribution of the different parameters. For example, this might be the current distribution over the total area of a single cell, and we investigate this in that way that if you have a single cell from a customer with a special customer flow field design, we build different electrically isolated segments within the active area, up to 68 segments, and then we contact these segments electrically, so we can measure the current distribution and we can measure the electrochemical impedance spectra inside a single segment. So we really know what happens at the local spot within a single cell. And this is the technique behind that. As I said, we have the cell inside. The cell is segmented into 68 segments. The 68 segments are connected with all of these cables to 68 potentiostats. The potentiostat can apply the frequency. And then we have 68 frequency response analyzers, which analyze the behavior of the fuel cell and the segments inside the fuel cell. Okay, this was the real cell level. Now, if you want to study the scientific effects of a fuel cell, you usually go down to smaller laboratory fuel cells, and this happens inside these labs. So you usually apply some accelerated stress test protocols, which are, at least in the Western world, are usually the DOE protocols from the US. And you do that to do accelerated stress testing of the different components within a single cell. Different components means it could be the catalyst itself, it could be the catalyst support, it could be the membrane, and of course the real fuel cell operation is also of interest. Within the real fuel cell operation, especially start-stop testing is very interesting for long-term testing of fuel cells. We did this, and then you get a lot of results. We can go into detail afterwards, because I see time is running out. This is about start-stop testing. So the main cause of degradation during start-stops is the change of the gases. So on the anode side, you have a change between hydrogen and air. And then you analyze the reduction of the electrochemical active area inside the fuel cell. And you can analyze the impedance spectra and the effects on a membrane and electrode level. This is combined with ex situ testing, so we can apply an SEM, for example, and look at the element distribution, what happens to the platinum, for example. We can combine this also with some ex situ analysis and do what happens during freeze-thaw cycling of different components and materials. And now my last point, just 1 minute, please, is, as I said, a last point of degradation could be contamination. So, for example, air pollution. And air contaminants will harm the fuel cell. So we do investigations on that, and I'd like to point out that we show our technique for doing that at our booth. The speciality of this is that we have, with our test setup, we can test up to 30 cells in parallel under different operating conditions with different materials, and then you can study the effects of air contaminants, for example, or if you're are going to do to develop new materials, you can test up to 30 materials in parallel. And this can be seen at our booth, and I'd like to invite you very heartily to have a good cup of coffee, good Freiburg roasted coffee, fair trade and ecological grown at our booth, and then we can discuss all of this later on. Thank you very much. Thank you for giving me the time.
Also, thank you from my side. here at the Technical Forum. Unfortunately, there is no time for questions here, but you can take all your questions to the booth to C58. You can take your questions there and you can have some fair trade coffee. That sounds excellent. Once again, thank you. Big hands, please, for Mr. Ulf Groos.